I'm picking up good vibrations.
In this video, we'll talk about the effects of sampling and the connection between Fourier transforms of continuous time signals and of sampled continuous time signals, which are discrete time signals. We will start with some motivation for sampling and some interesting effects that happen when we sample. Then we analyze one of the most basic functions, namely a cosine. After understanding the effects of sampling in the frequency domain for cosines, we will generalize our findings to arbitrary signals. Finally, we'll end with a celebrated Nyquist theorem that tells us what is the smallest rate that we can sample a signal and still be able to recover it.
Let us start with some motivation for sampling. Before the massification of digital computers, the main paradigm for treating signals was to do so in continuous time. Still today, if you buy a small radio and you open it up, chances are that it has no microprocessor. It has only electric components such as resistors, condensers, coils, and transistors. That is because it directly processes continuous time waves and outputs sound waves as a continuous time signal. To design these systems, the Fourier transform plays a tremendously important role. Indeed, since everything is in continuous time, we can use the good old continuous time Fourier transform as it was the case at the start of the 20th century. What happens if we use instead a digital radio? In this case, the continuous time waves are converted to a digital signal by a so-called analog to digital converter, represented here by the block A/D. The signal is then processed by a microprocessor which outputs a discrete time signal. That digital signal is converted to a continuous time signal by a digital to analog converter, represented here by the block D/A. These analog to digital and digital to analog converters are very simple operations. The analog to digital converter simply samples the continuous time signal at a fixed rate, which is called the sampling rate. This leads to a discrete time signal resulting from samples of the continuous time signal. The digital to analog converter simply holds constant in between sampling times the discrete time signal at its input. In this case, such a discrete time signal is the output signal of a radio. The Fourier transform still plays a very important role, but in this case, we need a discrete time Fourier transform or the discrete Fourier transform that we'll learn later on. These are discrete time versions of the Fourier transform which can capture phenomena in the digital world we now live in.
Does this work well? It depends on the sampling frequency. To illustrate this, let us take a song and play it with decreasing frequency. Now, one important note is that our ears can only interpret sounds in the range from 20 Hz all the way to 20,000 Hz. So for sound signals, we need a very high sampling frequency in the range of 20 kHz. Anything below that will cause our ears to notice. Let us then hear a song with decreasing sampling frequency. It is clear that the quality decreases as the sampling frequency decreases. A funny effect that we'll discuss later on is that as the sampling frequency decreases, we hear more and more low frequency or low pitch sounds. This leads to the following questions. How large should the sampling frequency be? Can we recover the continuous time signal from its samples? A similar effect happens if we undersample a movie. A well-known phenomenon is the wagon wheel or the car wheel effect. The wheels of a wagon or the wheels of a car seem to be stationary or even move backwards in a movie.
The two phenomena that we have just talked about, the car wheel effect in videos and distortion in songs, happen because we undersample a signal. More specifically, we will need a larger sampling rate to fully characterize a signal. Since we do not have this larger sampling rate, we misinterpret the true signal, either video or song, and believe it is some other signal. If we look at the picture shown here, we see that the samples at times -3 tau, -2 tau, -tau, 0 tau, etc., depicted here with a blue circle, can correspond to samples of two very different signals, the orange one and the blue one. The blue one might seem more natural, but the orange one might actually be the one. This is what happens in the video, for instance, of the car wheel effect, as we'll discuss shortly. Our brain interprets the samples of the signal that we see in terms of a more natural continuous time signal than the actual signal is. If you look into it from a purely mathematical perspective, actually we can find many other signals that have the same samples at times -3 tau, -2 tau, -tau, etc., but are different from the blue and orange ones depicted here. Thus, we conclude that in general, we cannot recover signal from its evenly spaced samples. Let us go back now to the car wheel effect to interpret what is going on. The movie that we are watching is nothing more than a sequence of images, typically around 24 images each second, which are played fast so that our eyes cannot distinguish between such a signal that has only 24 images and a normal continuous time one. Let us isolate the rapidly spinning wheel of a car and see in slow motion how these pictures are being taken. If we look at the images at the bottom from left to right, it will give you the illusion that the wheel is spinning anti-clockwise, whereas in the small animation of the wheel we have just seen, it was clearly moving clockwise. The wheel was moving clockwise, but simply too fast for the camera images to capture what was really going on. In fact, between two consecutive pictures, the wheel almost made a full spin. Let us now see that the sequences of images would also have been obtained from a slow wheel moving anti-clockwise. We obtain the same sequence of images with the two different signals, either the fast wheel spinning clockwise or the slow wheel spinning anti-clockwise. Although we cannot tell which one it is from the sequence of images, our brain assumes the simplest explanation, which would be that the wheels are spinning slowly anti-clockwise. This would mean in the original video that the wheels would be moving backwards with respect to the motion of the car. Although a simple explanation, this explanation does not correspond to the real signal.
However, many signals of interest are smooth and do not change very rapidly. In frequency domain terms, we say that the energy of the high frequency content of the signal is low. As an abstraction, we can say that the Fourier transform is zero outside of a given area. In that sense, the signal is band limited. We have seen that for arbitrary signals, we cannot recover them from its samples. But now we can refine the question that we have posed earlier to the following. For band-limited signals, can we exactly recover them from its samples? We will now use the tools that we know to answer this question, and the answer will be very elegant.
Let us answer the question of when can we recover a signal, first for a basic signal, namely a cosine. If we sample a continuous time cosine as depicted on the left-hand side, we extract a discrete time signal shown at the right-hand side. Let us take the Fourier transforms of these two signals. For the continuous time signal, we obtain two directs centered at omega c and minus omega c, where omega c is the angular frequency of the continuous time signal. For the discrete time signal on the right-hand side, if we take the discrete time Fourier transform, we get two directs centered at tau omega c and minus tau omega c, where tau is a sampling period. And this follows just from the fact that if we replace in cosine of omega c t by tau times k, we obtain cosine of omega c tau times k. Since we are in discrete time, we have to periodically replicate these two directs with the period 2 pi, so that the discrete time Fourier transform is a periodic function with period 2 pi. And this means that replicas of the signal defined in interval from minus pi to pi appear around 2 pi, minus 2 pi, 4 pi, minus 4 pi, etc. Note that since this signal is a cosine, we know that the Fourier transform is contained in a bounded interval from minus omega c until omega c in continuous time, so this is a band-limited signal. Let us see what happens as we vary the period. For that, it is convenient to define a few quantities. We denote by tau c the period of the signal, which we set to be fixed and equal to 2 pi. We denote by omega c the angular frequency of the continuous time signal, which is 2 pi over tau c, so omega c is 1. We denote by tau the sampling period, which in this plot is 2 pi over 8, but this one will change. And by omega c the angular frequency given by 2 pi, the omega s the angular frequency given by 2 pi over tau. If the sampling period tau is really small, say 2 pi over 32, then it is clear it is a cosine in discrete time. However, as the sampling period increases, say to 2 pi over 16, to 2 pi over 8, 2 pi over 4, or equivalently the sampling frequency decreases, it becomes less and less clear in the time domain that it is a cosine. Let us now increase further the sampling period to 2 pi over 3, 2 pi over 2, and 2 pi times 2 over 3. Something strange happens when the sampling period is 2 pi over 2. In this case, the sampling period tau is half of the period of the original signal. Tau c equals 2 pi, or equivalently, the sampling frequency omega s is 2. Which is equal to twice the frequency of the original signal, omega c equals 1. In this case, the directs at omega c times tau, depicted in blue, meet the directs associated with the periodic replications centered at 2 pi and minus 2 pi, depicted in orange and green, respectively. When the sampling period is 2 pi times 2 over 3, they even exchange positions, and the blue directs correspond now to a larger frequency than the green and orange ones. Since when we want to characterize the discrete time signal in time, we look into the interval from minus pi until pi, we now identify the signal based on the orange and green arrows. While up until now, for small values of the sampling period, when we look into the interval from minus pi until pi, we identify the signal from the blue arrows. Another funny feature is that for sampling period 2 pi over 3 and 2 pi times 2 over 3, the time domain signals are identical. If we ignore the colors of the directs of the discrete time Fourier transforms, they are also identically in the frequency domain. The colors are only there for us to understand where these directs result from. They play no role in the actual discrete time Fourier transform. So the discrete time Fourier transform for both sample signals at 2 pi over 3 and 2 pi times 2 over 3 are exactly the same as well. And this must be the case because the time domain signals are the same. So what can go wrong if the sampling period is too small, in the sense that it's smaller than half of the period of the continuous time cosine, and in frequency domain this strange effect happens, namely replicas of the directs around 2 pi and minus 2 pi, depicted in green and orange, show up in the interval from minus pi till pi. What goes wrong is that we will not be able to recover the original signal, which is characterized by its frequency omega c equals 1. Or in other words, we will not be able to correctly identify omega c. Let us see why this is the case carefully. For a small sampling period tau, say 2 pi over 32, or equivalently a large sampling period omega s, we can follow the following procedure to recover omega c. Given the samples that we obtain with sampling period 2 pi over 32, depicted here on the left hand side, we can compute the discrete time Fourier transform, and we expect that the directs that we obtain in the interval from minus pi until pi are centered around tau times omega c. So if we compute the distance of these directs to the origin, and we call it omega d, it suffices to divide omega d by tau, and we recover omega c. We can follow this procedure for almost all the sampling periods that we have seen, so 2 pi over 16, 2 pi over 8, 2 pi over 4, until 2 pi over 3. All these are smaller than half of the period of the signal, so smaller than 2 pi over 2. And this procedure will then still work. However, when the sampling period is larger than 2 pi over 2, namely 2 pi times 2 over 3, if we follow the same procedure, we do not recover omega c. We do not conclude that omega c is 1. As we discussed, barely anything changes when we change the sampling period from 2 pi over 3 to 2 pi times 2 times over 3. The samples of the continuous time signal remain the same, and the discrete time Fourier transform remains the same. So omega d remains the same. Omega d is the distance of the first direct to the origin. However, tau changes. So now, when we divide by tau, we get omega c equals 1 over 2. In this new case, tau is 2 pi times 2 over 3, whereas in the previous case, tau was 2 pi over 3. So we do not get any more omega c equals 1, we get omega c equals 2. This is not the continuous time value. This is not the value that we started with for the continuous time signal, so we do not recover the right signal with this procedure. We recover instead a lower frequency signal, namely cosine of 1 over 2 t, since omega c is 1 over 2. This signal is depicted here in the figure on the bottom left in red. This signal has the same samples of the original signal cosine of t when the sampling period is 2 pi over 3, as illustrated in the figure at the bottom left. This is exactly what happened in the animation of the cartwheel effect. When the sampling frequency was small compared to the frequency of the signal, we identified a low frequency signal, whereas the original signal was faster. What we have seen for this example of a cosine actually generalizes to arbitrary signals. Suppose that we have a signal xc and we take samples leading to a sampled signal discrete time xd of n. If we take the Fourier transform of xc, and let us say for simplicity that this continuous time Fourier transform is 0 outside of a given bounded interval, the discrete time Fourier transform of the sampled signal xd of n will be a periodic replication of a scaled version of the continuous time Fourier transform of the original continuous time signal. The scaling factor is the sampling period tau. So if the continuous time Fourier transform is 0 outside the interval from minus omega c until omega c, the discrete time Fourier transform of the sampled signal will be 0 for omega values slightly larger than omega c tau and slightly smaller than minus omega c tau. But since the discrete-time Fourier transform must be periodic with period 2 pi, there will be replicas of this discrete-time Fourier transform in the interval from minus pi and pi. So these replicas will happen around 2 pi, 4 pi, minus 2 pi, minus 4 pi, etc. Now, if the sampling period omega c is very large, meaning that the sampling period tau is small, the replicas will not interfere, will not be superimposed in the interval from minus omega times tau until omega times tau of the frequency of the discrete time Fourier transform. And we can recover the continuous time Fourier transform simply by looking into the interval from minus pi until pi of the discrete time Fourier transform. Recovering the Fourier transform of the continuous time signal is the same as recovering the original continuous time signal, as there is a one-to-one correspondence between the two. However, when the sampling frequency omega s is small, namely smaller than twice omega c, the replicas of the signal around 2 pi, minus 2 pi, 4 pi, minus 4 pi, etc. will be superimposed, they will interfere, and we cannot recover now the continuous time Fourier transform of the original continuous time signal, and therefore we cannot recover the original continuous time signal.
This leads us to the famous Nyquist theorem. If we have a signal which is band limited, in the sense that the Fourier transform is 0 for angular frequencies omega larger than a given omega c, the angular sampling frequency omega s must be at least twice as large as the largest angular frequency of the signal omega c. A few practical considerations before the end of this short video. The first is that we rarely have band-limited signals. However, very often the frequency of the signal does become very small as frequency increases. Moreover, often we can identify a band where the main frequency of the signal lies. Thus, in practice, we have some small distortion in the frequency domain, but it's not that significant and we can live with it. The second practical consideration is that the Nyquist theorem only sets a lower limit on the rate at which we can sample a signal. In practice, the larger the sampling frequency, the merrier.